This is Module 24 of Engineering Vibrations, an Introduction to Single Degree of Freedom Systems. Today's learning outcome is to solve for the transient response solution of the DEOM we came up with for a simple single degree of freedom system that was undergoing damping or had damping imposed. We're going to focus on the underdamped vibration solution at this point. And so here's where we left off last module. We'd already solved earlier in the course the undamped case, and so in this module we're going to focus on the solution of the underdamped case. I'll warn you ahead of time that there's quite a bit of math in this module. The good news is that you can stop the recording, go back and review it, and maybe do some review of your earlier math days to make sure you can follow along. So here's the critical damping ratio. I'm going to rewrite the roots of the characteristic equation that I show up here. And so now that I have the critical damping ratio defined, I can substitute in for the first term, and in terms of zeta, the damping factor or the damping ratio, and I can also substitute it underneath the radical as well. And so my characteristic equation roots now look as shown here, and then I can factor out the underneath the radical the omega natural, right? Because I have the omega natural squared in both terms, and so I end up with minus zeta omega natural plus or minus omega natural times zeta squared minus 1. And we said that for zeta less than 1, this is an underdamped system. And so what that means is zeta squared minus 1 is going to be a negative number underneath the radical, underneath the square root. And so when I take that the square root of that negative number, I'm going to get an imaginary value. And so I have I plus or minus I times the value of omega natural times, now since I took since it's a negative number, I took the minus 1 out, the square root of that, it ends up flipping and becoming 1 minus zeta squared, which is a positive value. All right, so there is my rewritten roots for the underdamped case. Now I can define the damped natural frequency as the coefficient of the imaginary I term. And so omega damped is defined as omega natural times the square root of 1 minus zeta squared. And again, 1 minus zeta squared is a positive number. And so we see that it's going to be less than 1. And so the damped natural frequency is going to be a lower number than the omega natural. And so the damped frequency is going to be less than the frequency of the undamped system. And then if I look at the damped period, since the damped natural frequency goes in the denominator, the damped period becomes larger than the undamped period. Okay, so we defined the damped natural frequency. There's my new roots. Instead of keeping the whole value omega natural times the square root of 1 minus zeta squared, I've substituted in omega d here, the damped natural frequency. And so my general solution now becomes, I have two roots, two lambdas, and so my solution was a e to the lambda t. I've got two roots, so here's the first one times some undetermined coefficient a1 for the first root, where we're using the plus here, and then a2, a second undetermined coefficient, times e to the minus zeta omega natural minus I omega dt. Okay, so here's the general solution again. I've just collected terms here. I've taken the e to the minus zeta omega natural out and multiplied the remainder for both terms inside the parentheses, inside the brackets. And again, like we've seen earlier in the course, I'd rather work with sines and cosines than complex exponentials, and so I can use Euler's formula, as I did before, to change the solution into a function of sines and cosines with two different undetermined coefficients, b1 and b2, as shown here. So now with this general solution, how am I going to find b1 and b2, the undetermined coefficients? Stop the video, ask yourself that, and then come on back. So what you should say is we're going to apply the initial conditions to solve for what the undetermined coefficients b1 and b2 are going to be. And so let's take the initial condition for the displacement, y at time 0, which we said was y sub 0. So we have e to the time is equal to 0, so this zeroes out. This time is 0, this time is 0. And so we've got e to the 0, b1 times cosine 0 plus b2 times sine of 0. And e to the 0 is equal to 1. Cosine 0 is equal to 1. Sine 0 is equal to 0. And so we find that one of the undetermined coefficients, b1, is equal to y sub 0, the initial displacement. Now we want to find the other coefficient, b2. We have an initial velocity condition, and so what I've done here is I've taken the derivative of this function. First, I take the derivative of the e to the minus zeta mega natural t. Therefore, the function of time, or minus zeta mega natural, comes out front here, times e to the zeta omega natural t. That's times the second portion here. And then we take, as you recall from your days of taking derivatives, we take the derivative of the second term times this. So there's my e to the minus omega natural t. The omega d comes out because in each case, because it's the function of t. And so it's out front here. When I take the derivative of cosine, it becomes minus sine. So that's where the minus sign comes from. And when I take the derivative of sine now, that becomes cosine, and it's positive. So that's the derivative, a little bit of refresher on taking derivatives. Now that we have that, I can put in, that's the general function for the velocity y dot. Now I can put in the initial condition where time equals 0. So this is going to go to 0, 0 t here, 0 here, 0, 0, 0, 0. And so what I end up with is e minus zeta mega natural e to the 0, where e to the 0 is equal to 1. Then I've got cosine of 0. We know what b1 was. We solved for it. That was equal to the initial displacement. Cosine 0 is equal to 1. Sine 0 is equal to 0. E to the 0 is equal to 1 again. Sine 0 is equal to 0. E to the 0 is equal to 1. And finally, cosine of 0 is equal to 0. So that's where we ended up. And we can solve then. We have y dot sub 0 is equal to minus zeta omega natural y sub 0 plus the natural damped, or the damped natural frequency omega d times b2. And so with that I can solve for b2, and it ends up being this. So I've now got both b1 and b2, my undetermined coefficients, and I can sub those in, so I end up with a response solution for a system undergoing free damp motion for underdamped conditions. And that's it right there. So again, a little bit of math, but you should be able to follow that through. And that's the end of this module. As a summary, we did the transient response solution for a single degree of freedom system undergoing free underdamped vibration. And see you next time.